Hello, kiddies. Alright, so negative binomial random variables. X is a negative binomial random variable with parameters r and p if it models the time until the rth success in a sequence of independent Bernoulli p trials. Okay? Know this. With all of these random variables we're covering, be sure to know the meaning of a negative binomial random variable. It models the time until the rth success in a sequence of independent Bernoulli p trials. Why is it called negative binomial? It's because it's sad. Alright, so here you can think of, maybe we'll do a bunch of trials, okay? Trial number 1, trial number 2, trial number 3, trial number 4, and so on. And when I perform these trials, maybe I fail the first time. Maybe then I succeed, and then maybe I fail and fail, and then I succeed and I fail. Maybe I succeed again, and then here finally I succeed for the rth time. Okay, maybe down here I'll put the success numbers. Okay. Here's the time of my first success. Here's the time of my second success, third success, and then rth success perhaps occurs here on the kth trial. Okay, so what we're interested in is knowing the probability that this negative binomial random variable takes on the value of k. Well, to think of it, to build this probability mass function, note that in order for this to happen, you must observe a success on the kth trial. Okay, and all these trials are independent, so I'm just going to multiply by probability p, by the way, because p is the chance that I see a success on the kth trial. Now, forget about this. Now, what I have to see is I have to see r minus 1 successes in the previous k minus 1 trials. What's the what's the probability that I see that? Well, that's just a binomial probability, isn't it? Okay, so I've got k minus 1, choose r minus 1, times, I'm going to take p raised to the r minus 1 times 1 minus p to the k minus 1 minus r minus 1, right? See that? So actually this simplifies a little bit. If I have this exponent just becomes k minus r. I think this just simplifies to this. Okay. And of course this is for k in the set r to r plus 1, r plus 2, etc. Okay. Note that the chance that x equals k equals 0 for k less than r, right? You have to perform the experiment at least r times to see that many successes. Okay. All right, let's go ahead and get the mean and variance, and then we'll do an example. There's several ways to do the mean and variance. Here's the slickest, easiest way, and we'll do that because that's what I'm about. I'll let you guys do harder stuff in your homework. I want to find the expected value of this negative binomial random variable. Okay. Well, tell you what, there's an easier way to express that negative binomial random variable, and that is, note that the time until the rth success, that's like looking at r geometric random variables back to back, right? You have to wait for the first success, then you have to wait for the second success, then you have to wait for the third success. You're doing a whole bunch of, you're effectively looking at the sum of R geometric random variables. YK are, these are independent geometric P random variables. Okay? You can see that if you look back over here at this picture, I think. Right? The time until the first success is a geometric random variable with parameter P. And then you have to wait until the next success, right? That's going to be another geometric random variable with parameter P. And then another one plus another one. The total time is the sum of those times. Okay. Now, life is going to be really easy because we know from before that this is just the sum of the expected values. Right? And now all of these things have the same distribution. I know what they are. It's right. Each one of these is geometric, so that's the mean. And I'm summing up R of these things. So that's just R times 1 over P, or R over P. Okay? Simple, right? It's just, you know, it's exactly what you'd expect. Geometrics, you know, if R was 1, this would reduce to the geometric random variable, right? You'd have a mean of 1 over P. Okay, so what about the variance? What about the variance? Well, here's something that you'll prove, and we've used this before, but it makes life so easy. We're going to use it here too, but so if Z1, Z2, etc. to Zn are independent, they have to be independent random variables. And let's say C0, C1 up to Cn are constants. Then the variance of this combination like so, this linear combination of these variables just turns out to be the sum of the CI times the variances. Okay, and note that that C0 goes away. C0 goes away. You prove something like this in your homework, right? Adding a constant to something that varies doesn't change the variance. And that makes a lot of sense, because when you add a constant to a random thing, you're just shifting where the random thing is located. Adding a constant to a random thing is going to change the mean, but it won't change the spread outiness of that distribution. Okay, so that's why you don't see that constant appearing over here. All right. Okay, so then I'm going to use this. Maybe we'll call that a lemma. And I want to get the variance now of this negative binomial random variable. And again, I'm going to express it as the sum of R geometric P random variables. Okay, and then by above, since these are independent, since these YK, since the YK are independent, this is the sum of the variances, right? Now, what's the variance of any one of those guys? Okay, that is, what's the variance of a geometric P? Don't we know this? It's 1 minus P over P squared. And I've got R of these things, so it's just R times 1 minus P over P squared. Fantastic. Okay, so let's do an example.